Hello everyone, I'm so glad that you could join us today for this lesson on calculus graphs. So today, what are we doing in the lesson? I hope that you are ready and you're ready to learn, and I hope that you've got your books with you as well, because I'd like you to take down a few notes and a lot of little concepts that you need to make notes of. You will go through in today's lesson, so it's important that you have your pen and your notebook with you, especially when I give you a chance to do examples as well. All right, so today we're going to be looking at finding the derivative and then interpreting the second derivative. All right, so we're going to be looking at those two things, finding and interpreting the second derivative, and then we're also going to look at sketching cubic functions given the derivative graph. Okay, so when we're talking about sketching cubic functions, some of you may have already done this at school. We will go through briefly the concept of how you sketch a cubic function, but today what we're really interested in is if you've got the second derivative, the derivative graph, how can you then use the derivative graph to sketch your calculus graph? So that's really what we're going to be concentrating on when we're talking about sketching of cubic functions in today's lesson. Okay, so what are some of the key things that you need to remember? Okay, now we talked a little bit about the second derivative. I mentioned it in the opening. Well, what is the second derivative? And if you have a look, you'll see that the second derivative is defined as the second derivative of a function is the derivative of the first derivative. So you remember your first derivative is a function as well. So when you derive that function, so maybe your first derivative will be f prime x, your second derivative will be the derivative of that function. What the second derivative tells you is the change in gradient of the original function. So your original function is f of x, and your second derivative tells you the change, indicates the change in gradient of your function f of x. It will make more sense when we look at examples. The sign of the second derivative tells us if the gradient of the original function is increasing, decreasing, or remaining constant. Okay, and again, we'll look at a few examples and explain that in more detail. What I would just like to remind you of is the symbols we use to indicate the second derivative. As you saw, it will be f double prime x, so it indicates we're taking the derivative of the derivative function. Or another way that you might come across, or you might see this one, the differential operator of the derivative function. So if you see that, that also means you're taking the second derivative, okay? This can also be written as, all right, and we're going to come down here now. This can also be written as this. This is not a square, right? The 2 indicates that you're taking the second derivative. So you're taking the derivative of y with respect to x twice. That's what the 2 tells you. It does not tell you that you're squaring anything there. Okay, so those are the different symbols and notations you might see for the second derivative. Now, what I would like you to do, I've got an example on the screen, and I want to go into detail explaining the concept of second derivative and the derivative function and how they relate to the original function. So before I go into that detail, I want you to just get familiar with the function I'm going to be talking about. So I'd like you to take down this example that's going to be on your screen now, where you have to calculate the second derivative of f of x is equal to 4x squared, and then I've asked you some questions on that. So I'm going to give you 2 minutes to just have a look at this, take it down, and jot down a few notes. All right, guys, so we're going to now go through this process of working out the second derivative, and more importantly, I want to look at how the second derivative, the first derivative, and the function itself are all related to each other, okay? So you were given this example to consider where you had to calculate the second derivative of the function f of x is equal to 4x squared. So the first question posed to you was to calculate the second derivative. All right, so in order to do that, we first need to work out the first derivative. So the first derivative f prime x is going to be equal to 8x. So we take our power, we multiply it by the coefficient in front of the x squared. So 2 times 4 gives me 8. And from the power 2, we subtract 1. So we get x to the power of 1. The second derivative, I now need to derive the function 8x. So when I derive 8x, remember your power of your x is 1. So to derive that, 8 times 1 is 8. And x to the power 1 minus 1, so x to the power 0 is just 1. So therefore my second derivative is 8. Okay. You then, now that you've looked at your function f of x, you've got your derivative f prime x, you've got your second derivative, I've asked you what type of function is each of them. So f of x, you can see we have a square, right? So that we know is the definition for a quadratic function or a parabola. So f of x is a quadratic function or it is a parabola. Now, if you look at your first derivative, you get f prime x is equal to 8x. So that is, we've just got x to the power of 1. That is a linear function. So it's a linear function, or we say it's called a straight line, right? And then you look at your second derivative and you've got just your second derivative is equal to 8. Well, that's also a linear function. It's got a constant gradient of 0. So it's a linear function, a straight line of y is equal to 8. That's going to go straight through the y-axis at the point 8. Now what I'm going to do is we're going to have a look at the sketches of each of these functions, all right? Because remember all of them, f of x, f prime x, and your second derivative are all functions, okay? So on your screen you'll see that I've got each of them sketched for you. So let's go through them and see how they relate to each other. So in black, we've got the original function f of x is equal to 4x squared. And then in orange, you'll see that you have your first derivative, which is f prime x is equal to 8x. So that's a straight line. And then we've got our other linear function, our second derivative, equal to 8. And that's a straight line with a gradient of 0 going straight through the point y is equal to 8 on your y-axis, as you can see in purple. Okay, so those are the three graphs. Now let's look at how they relate to each other. And this is the important part. Okay, so how do they relate to each other and what points on each of them sort of lets us know what's going to happen to the other graph. Okay, so the important function here is f of x, and we want to see how the first derivative and second derivative relates to f of x. Now, if I were to draw tangents to f of x to the left of 0, you can see that your graph is turning at the point 0, 0, right? So if I were to draw tangents to the left of 0, 0, I will see that my tangents have a negative slope. That tells me that my graph will be decreasing. Similarly, if I draw tangents to the right of 0, I see that I have a positive slope, which tells me, so tangents drawn to the left of 0 will have a negative slope. Tangents drawn to the right of 0 will have a positive slope. The positive slope tells me that the graph f of x is increasing for x is greater than 0. All right? Now have a look at how that relates to your function, the first derivative, your derivative graph, f prime x is equal to 8 of x. Now what you'll notice is beyond the point to the left of the point 0, so for x less than 0, so that's to the left of your axis, you will notice that your function 8x in orange is below the y-axis. So that means for x less than 0, your derivative function is negative. And it makes sense, right? Because if you look at your original f of x function, your parabola, you will see that tangents drawn to the parabola when x is less than 0 will have a negative slope, right? And remember that the gradient of your tangent is equal to the derivative of your graph, okay? So therefore, you can see it makes sense that if my gradient is going to be negative for x is less than 0, then therefore your original function should have a negative slope when x is less than 0, and it should be a decreasing function, as you can see on your graph. Decreasing function, remember that means that as your x values increase, your y values or your function values decrease. All right, so up to the point 0, when x is less than 0, we see that our first derivative is negative. To the right of 0, look what happens to the right of 0. Here we can see that our function in orange, your derivative function, is above the x-axis. When it's above the x-axis, you know all your y values are positive. So if you're looking for x greater than 0, you will see that your first derivative is positive. Your first derivative there is positive. In other words, it lies above the x-axis, okay? So therefore, again, you can make that comparison and you can see that when your first derivative is positive, then your original function f of x, what's happening to it? It is increasing, and the slope of your gradient is positive. Now, how does this relate to your second derivative graph, which is always, as you can see, constantly greater than 0. So throughout this discussion, you can see that your second derivative is always positive. It always has the value of 8 when x is less than 0 and when x is greater than 0. And what does that tell us? Well, the second derivative being greater than 0 tells me that my first derivative is going to be an increasing function. And you can see that it is. We have a positive gradient, so it's an increasing function. And also what it tells you, interestingly enough, if your second derivative is positive at the turning point of your graph. Now here, and I'm just going to erase some things there so that you can see what's going on. My turning point of this graph is at the point 0, 0. Okay, so my turning point, my parabola turns at 0, 0. Okay, so turning point is 0 and 0. Okay, so with my second derivative being positive, greater than 0, so my second derivative is positive at the turning point of the original function f of x, that tells me that I'm dealing with a minimum or a local minimum. So, a minimum turning point. So not local, just minimum turning point. So that's if your second derivative is greater than 0. So it tells you two things. It tells you that your gradient function is increasing. It also tells you that you have a minimum turning point. And remember, another way you can tell a minimum turning point is your gradient changes from a negative to a positive on either side of your turning points. Okay. All right, so that's quite a lot of information to digest, okay? It is an important concept because it's something we'll be coming back to in today's lesson, and it's also an important thing for you to understand for exams and tests and that kind of thing. How does the second derivative, first derivative, and function all relate to each other? And they do relate to each other, so I hope that you understand that. I'm going to give you a bit of time to think about that as we take a quick break, and then we'll come back and do more questions. Welcome back, everyone. So remember, in today's lesson, we're talking all about calculus graphs. Specifically, we're looking at the derivative graph and the graph of the second derivative as well as we did just before the break. Now, I just want to quickly go back to what we were talking about, looking at the sign of the second derivative and making conclusions about the original function and the turning points of the original function. So we said that if your second derivative is greater than 0, that would then mean that you have a minimum turning point of your graph. So if your second derivative is negative, less than 0, that will tell you that you have a maximum turning point. And if your second derivative is equal to 0, that will tell you that you have a point of inflection. It's something we will come back to. I don't want to discuss this too much now. We'll talk about this a little bit later on, but that tells you you have a point of inflection. All right. Okay, so what we're going to do now is quickly go into some questions, which is why I just wanted to remind you about what your second derivative tells you, because we might need this information as we look at our first question for today. I'm going to give you some time just to take down the key information and jot down some notes of how you will attempt to do this question. So we will give you 2 minutes to have a look at this. All right, everyone, so hopefully you had enough time to take that question down just so that you have the sketch with you as we go through these questions. I know it wouldn't have been enough time to do the whole question, but hopefully with my explanation and with the diagram, it will make everything a lot clearer. All right, so you were given the graph of the derivative. You were told that sketched below is the derivative graph g prime x is equal to minus 2x plus 2. So we identify that that is a linear function. You are told that the x-intercept is 1, but you can see that on your graph as well, and you can see that the y-intercept is 2. Okay, so let's just look at this graph before we look at the questions and see what type of linear function it is. I can automatically see, you know, because of our knowledge of linear functions, we can see that it has a negative gradient, all right? So therefore, it is a decreasing function. So we can already see that. The gradient of that straight line is negative. It's a decreasing function, okay? We can also see that if we look beyond the point 1, so if I look to the left of 1, so x is less than 1, and then to the right of 1, some interesting thing happens. We see that for all values for x less than 1, your graph lies above the x-axis. So therefore your function values are all going to be positive. And then for x greater than 1, your graph lies below the x-axis. So therefore all your function values are negative. All right. So we just noticed that there's some interesting things happening at the point 1, to the right of point 1, and to the left of point 1. Okay. First question says, what type of function is g of x? So you were given the derivative graph, you're being asked questions about the original function. Well, since your derivative graph is linear, your actual graph, your g of x, it must be one more than that, so it's got to be quadratic. So this is g of x would be a parabola or quadratic function. All right. Also, just interestingly to note, right, we see that the sign of our derivative is negative. Okay, so what that tells me is already I'm thinking, well, my parabola then must be a parabola with that looks like that. So the value of a must be less than 0. So if I was doing a defining equation, ax squared plus bx plus c, the value of a must be negative, because when I derive that function, I see that my derivative is starting with negative as well. Okay, so that automatically tells me that's the kind of shape that I'm going to be looking at. Okay, so I start thinking about those things. They say, for which values of x is g of x increasing? Okay, so we saw that the gradient graph, this g prime x equals minus 2x plus 2. We saw that that graph was positive for x less than 1. So a positive for x less than 1 tells me for which values of x is g of x increasing. Well, g of x is increasing when x is less than 1, because at that point, okay, if you want a reasoning here, that's because my gradient, the actual values, the function values, you can see that it lies above the y-axis. So therefore, my gradient is positive when x is less than 1. For which values of x is g of x decreasing? So decreasing would be when my gradient function is negative, and we see that it's below the x-axis for all values of x greater than 1. So therefore, g of x itself will be decreasing when the gradient is negative. All right. So if I go to the little sketch that I drew for you here, what we're saying is, so we have a point here, right? That's the turning point. And we can see that to the left of that turning point, all right, so if I draw a little tangent to that graph, to the left of that turning point, what's happening? The graph is increasing because the gradient of your tangent line will be positive. Then to the right of your turning point, the gradient is negative. Therefore, you have decreasing values, and that's really what we explained in parts B and C. All right. Part D says, what is the x-coordinate of the turning point of g of x? Well, we know there's two ways that we can work this out. We can actually look at the second derivative, or we can simply say, well, since we can see the gradient at the point x is equal to 1 is changing, the gradient is changing from positive to negative, from positive to negative. Therefore, that point, x is equal to 1, must be the x value of the turning point of my function. So the x-coordinate there would be x is equal to 1, and that's because your gradient is changing. Or if you look at your second derivative, if you wanted to go that far, right, if you take the second derivative, right, so we derive g prime x, we're going to get minus 2. Okay, so I'm deriving that function, I get minus 2. And we can see that that second derivative is always negative, and at that point, when x is equal to 1, you will see that your second derivative is negative, and therefore you're dealing with a maximum turning point as well. All right, so is it a maximum or minimum? It is a maximum, and there's two reasons. We can see that our gradient is changing from positive to negative. So when we go from a positive to a negative gradient, we have a maximum turning point, or we said since the second derivative is negative at that point, we have a maximum turning point. Okay, now we have to make a rough sketch. Okay, so a rough sketch, that means we don't have all the exact values. So we're going to quickly draw a rough sketch of what g of x could look like. The one thing that we know about g of x is that at x is equal to 1, the graph is going to turn and it's going to have a maximum turning point. So we know that the graph is turning at that point, so therefore we can put that point down. We know that it's going to have this type of shape as I've shown you before, where we have a maximum turning point, so therefore my sketch graph is going to look like that. All right, we don't have any other specific values, we don't have x-intercepts or anything like that. It's just a rough sketch of what a g of x could possibly look like. All right, okay, so I hope that you understand this concept of how the derivative, the second derivative, and the function itself is all related to each other. Okay, so we're going to look at another question to give you time to understand this, but for now, I want to just quickly talk about sketching a cubic function. So before we carry on with derivative graphs, let's just talk about sketching a cubic function. And what I want to do now is I'm going to go through the steps of how you sketch a cubic function. These steps are standard, they do not change. So if you've got your pen and notebook with you, this is where you want to make notes of this. I'm going to give you some time, maybe a minute or so, just to take this down, but let's go through the steps quickly before you take them down. So the general method to sketch a cubic graph, this is what you do. You first consider the sign of A and determine the general shape of the graph. So if A is greater than 0, so remember when we're talking about a cubic function, you've got a function defined by y is equal to ax cubed plus bx squared plus cx plus d. So A is the coefficient of x cubed. All right. So if A is greater than 0, then you're going to have a graph that has a maximum turning point and then a minimum. So that's the shape. All right. If A is less than 0, you're going to have a graph that has a minimum turning point and then a maximum turning point. So that's what we say when we say consider the shape. So you already in your mind have an idea of what the graph's going to look like. You then determine the y-intercept by letting x equal to 0. You then determine the x-intercepts by letting y equal 0 and by factorizing using most of the times factor and remainder theorem, but not always, and you solve for x. You find the x-coordinate of the turning points of the function by letting your derivative equal to 0 and then solve for x. And then remember, a stationary point can either be a local maximum, a local minimum, or a point of inflection. Now, at a point of inflection, that is the point where your concavity of a curve changes, all right? You will then determine the y-coordinates of the turning points by substituting the x values from point 4 into f of x. You will then finally plot the points and draw a smooth curve. So guys, what I want to do here is just give you a chance to take these notes down, just in case you need the step-by-step pointer. I'm going to give you a minute to quickly jot down these key points, and then we'll take a quick break and come back and do some questions. But for now, just a minute to take down these key points. Okay, everyone, so I hope you've got down all those steps for sketching cubic graphs, but remember our main focus for today's lesson is looking at the derivative function and using that to help us sketch cubic functions. But now that you have these points down, you will be able to draw your cubic functions yourself. All right, we'll take a quick break, come back and carrying on with the same. Welcome back, everyone. So I hope that so far you've learned quite a bit and you understand a lot more about how you can use your derivative graph to help you sketch your original function. Okay, so we're going to discuss a lot more about that in this next segment, and we're now going to look at sketching of a cubic function. So far we've only looked at quadratic functions and their derivatives, which have been linear graphs. But now we're going to look at a cubic function and its derivative, which is a parabola or quadratic function. So I want to really give you time here to just take this question down, get down as much of the information as possible, and you can attempt it, but I don't know if you'll have enough time to do that. But most importantly, get all the key points down, make a rough sketch, a very rough sketch. It doesn't have to be exactly to the T measured, etc., etc. Okay, so I'm going to give you 3 minutes to have a look at this, and then we'll come back and do it together. Okay, everyone, so let's have a look at this question where we're talking about being given the derivative graph and then having to sketch the original function. Now here what you will notice is that you've been given your derivative graph as a quadratic function. So that tells me that the original function h of x must be cubic. It's always 1 up. So if your derivative is quadratic, then your original function is going to be cubic. Okay, so you were given that in your graph, you've got the x-intercepts, and they told you that those x-intercepts are -5 and 1, as you can see drawn. And they said, draw a sketch graph of the original function h of x, and then they told you what the function values of the original function is at -5 and at 1. So we'll come back to that. But for now, let's just discuss the derivative a little bit more. Okay, so we noticed that we have a derivative parabola a derivative function that is a parabola. So I know that in my defining equation, just by looking at the shape of this graph, all right, parabola. So just by looking at the shape of this graph, I can automatically see that A must be negative because we have a maximum turning point. So therefore, this derivative graph must have an A value that's negative. That already starts telling me that my cubic function, because remember they are related to each other, my cubic function defined by y is equal to ax cubed plus bx squared plus cx plus d must also have a coefficient of a different a now, but that a must be less than 0. So just to avoid confusion, a1 would be the a that we're referring to of the quadratic function, and then a itself we're referring to a of the cubic function. So a must also be negative because my function of the derivative graph is a graph with a maximum turning point. So I start thinking about the shape of a cubic function that has the coefficient of x cubed as a negative, and I recognize that the shape must look like that. So this is just little aids that help you more and more in your understanding of how to sketch this graph without being given the actual graph. So these little pointers help you and point you in the right direction. So the fact that I've determined that A is negative already tells me what type of graph I'm looking at, and from there I can already get a whole lot of information. But let's rather go back to the derivative graph and get information from there. We see that we've got two x-intercepts. So this is what we're saying. At your x-intercepts, it's where your derivative function is equal to 0, because obviously the corresponding y values are 0 at your x-intercepts. Okay? Now, can you think about when you're sketching a cubic function, when do you say let the derivative graph let the derivative equal 0? When do you do that? You're told to do that when you're looking for the stationary points, the turning points. So it makes sense that the x-intercepts, which is the point where your derivative function is equal to 0, those x-intercepts will be the x values of the stationary points of your original function. So these x-intercepts are where your derivative is equal to 0. So therefore, these are points where it is the stationary point for the original function. So it's the x value of the stationary points, and on the other side, when x is equal to -5, that's also a stationary point. Okay, so it tells me where my graph is going to turn. So I've got two turning points. My graph is going to turn at -5 and 1. We've already determined that because our function h prime x, our derivative function, is a parabola with a maximum turning point, we've already determined what the shape is going to look like. So that's almost half the work done. All right. Now they add to that h of -5 is 2. What does this mean? This tells you that your function value on your original function, h of x, your cubic function, your function value is 2. Your y value is 2 when x is -5. In other words, this is a coordinate on your graph h of x. So that's a coordinate. The other coordinate on your graph h of x, when x is 1, y is 6. So when x is 1, y is 6. Now what's special about minus 5 and 1? Do you remember? Minus 5 and 1, those were the stationary points of my cubic function. That's where the graph was going to turn, the graph of h of x. Those were the stationary points. So what they've really given you is they've given you the stationary points. They've given you the x and y values of your stationary points. All right. So that should make it quite nice and easy for us to sketch the function h of x. So let's have a look, and we're going to just draw this on the sets that we have already. So on this graph that we have, we know that the graph is going to turn when x is minus 5 and when x is 2. So that's going to be a point when x is minus 5 and y is 2. It's going to be there in line with that point, all right? All right, we also know that the graph's going to turn when x is 1 and the y value is 6. So when x is 1 and y is 6. So we're going to say that that is somewhere up there. Okay, now this is when we need to look at the shape, right? This is where the shape becomes important, because I know we're first going to have a minimum turning point and then a maximum turning point. So therefore, that tells me that my graph, the shape of the graph is going to look like this. We're going to first have a local minimum. It's going to cut through the axis, it's going to turn and then come down again. Okay. Another way you could have done that, so I've drawn a rough sketch already, right? So I could already tell what it's going to look like. But the other way you could do it is you can look at the sign of your derivative at the point before minus 5 and at the points above minus 5, okay? So I see that my gradient function is negative. Can you see that? It's below the x-axis. So your derivative is negative when x is less than minus 5. And then I notice that my graph moves above the axis when x is greater than negative 5. So you can see that whole part there is above the axis, and that's all the way up to there. The graph is still above the axis. So therefore, your derivative is positive when x is greater than negative 5. So that tells me, because the sign of my gradient is changing, it's going from negative to positive, from negative to positive. It tells me that the point minus 5 is going to be a minimum turning point. All right, so if you didn't know what the graph was going to look like, that tells you your point minus 5 is going to be a minimum value, a local minimum, because remember we call it local minimum because there are values that are less than that. Okay, now have a look at what's happening at the point x is equal to 1 and then to the right and left of x is equal to 1. So we can see that our graph of the derivative when x is less than 1, we can see that the graph is, so when x is less than 1, the graph is positive. So h prime x is positive. Obviously, it's between 1 and minus 5, but we're just looking at 1 now. We can include, for completeness, it's between minus 1 and 5. So from that point 1 up to minus 5, your graph is positive. It's above the axis. And then to the right of the point 1, so your derivative to the right of the point 1 is negative. It then falls below the axis. So what's happening? At the point 1, your gradient is changing from positive to negative. So if your gradient is changing from a positive to a negative, that implies that that point, x is equal to 1, must be a local maximum value. All right. So hopefully you understand that, and hopefully you all arrived at the same conclusion when dealing with your derivative graph, when you're given your derivative graph, and then relating that to your original function. Okay, so this is really just pointers and tips of how you can analyze and really study the derivative graph to help you get key points to draw your original function. And here we looked at a cubic function, but remember, any graph can have a derivative. So we know that if we take the derivative of a quadratic function, we can get a straight line function. Okay, so you've just got to look at what your question is telling you. When we were looking at the case here where we had quadratic function as my derivative, that tells me I have two stationary points, which tells me I'm dealing also with a cubic function. So just to wrap up quickly, for your derivative equal to naught, so in other words, for your stationary points, all right, there's certain things you can remember. If your derivative, your second derivative, is negative, so if the sign of your second derivative is negative, you are dealing with a maximum stationary point. If the sign of your second derivative is positive, greater than naught, then you are dealing with a minimum stationary point. If your second derivative is equal to naught, that tells me it's a point of inflection, and that means the concavity changes. All right, so around your points of inflection, your concavity changes. So your graph can go from concave up to concave down, or the other way around. All right, so that's really just describing what happens at your stationary points, and really where this is useful is when you are given the graph of the derivative and then you are asked to draw your original function. Okay, I hope that you found today's lesson extremely useful, and I hope to see you again and hope that you will join me again for another lesson. Until next time, cheers.